Okay, so as in the last video we have derived the unit for the potential difference, and we have seen the nature of the potential difference, and that topic was very important in terms of MCQs. I have told you guys three things in though not three, however four things in that. Initially that was a scalar quantity, secondly it was a dot product, thirdly it has a unit of volt, and volt is also a unit of EMF, electromotive force, electric potential, and of course the SI unit of potential difference. Lastly or finally, I told you about the dimension that was equal to ml2 t minus 3 a minus 1. As you can see here, let me highlight this, ml2 t minus 3 a minus 1. Now how did we get this dimension? Today we'll be discussing about that. How did we get this ml2 t minus 3 a minus 1? We're going to derive the dimension, or we're going to take out the dimension for the potential difference by using its formula, which is electric field intensity dot del r. So wait, let me write the formula here. We can derive the dimension from here, right? Dimension for potential difference. Potential difference. Alright, today we'll be deriving the dimension for the potential difference by the formula, by using the formula. We know that the potential difference, which is denoted by V, volt, is equal to the dot product of electric field intensity and the displacement, which is a vector quantity as well. And in the electric field intensity, when we were discussing about electric field, all right, the electric field was equal to what? It was the ratio of the force per unit charge. It was the ratio of the force per unit charge. And let's put this force per unit charge in this equation, in first equation. I am giving it a name of first equation. All right, first equation. So let's put this electric field formula in the first equation. So V is equal to, instead of electric field intensity, I can write force per unit charge, and of course del R, right? Now see, the unit of force is what? It is Newton, upon the unit of charge is Coulomb. However, the unit of the displacement is meter, right? Now what's the dimension of Newton? First let us derive that. All right, so we know that F is equal to ma. Here we got the Newton unit, right? So from here we will be deriving the dimension for the Newton. So F is equal to ma, which was the second equation of motion, right, which was given by, of course, Newton. So F is equal to m means kg and a means meter per second square. If I do write dimension for it, F is equal to kg means m, which is representing the mass, meter means L, which is represented the length, and of course T minus 2, since this second, when we're gonna up, it will have minus sign, right? So T minus 2, this is the dimension for the force, right, which is of course equal to Newton. So of course I can now put this dimension in this formula, right? So wait, before putting this dimension of the force or Newton in this formula, let me tell you what Coulomb is equal to. 1 Coulomb is equal to 1 ampere into 1 second. So 1 ampere into second is what we call the Coulomb equal to. So let me write this here as well. Coulomb is equal to ampere into second. Ampere into second. This is the most important topic in terms of MCQs. They're gonna ask you a lot of questions from it. Alright, now we have got the dimension for the Newton, that is equal to, of course, m, right, L, and of course T minus 2. and the dimension of M would be what? It would be of course L, since it represents the length, upon ampere means A, right? And of course second means time. Now we need to take these both up, alright, means they both will gonna get minus sign. So V is equal to M L T minus 2, same I'm writing this, right? L. Now I'm just going to take these up, they're gonna have minus sign, so A minus 1 and T of course with minus 1, right? Now simplify it, what we'll get, M we have of course 1, so it will gonna have 1, write 1 or not, it would not gonna matter a lot, because M is already there, it represents that it has a 1 power. And L, now see L are 2, so of course you need to write 2 power, then minus 2 minus 1, minus 2 minus 1 equals to minus 3, so T minus 3, and of course A minus 1, A minus 1. Now see what's dimension of the potential difference is ML2 T minus 3 A minus 1. This is what we discussed yesterday as well. ML2 T minus 3 A minus 1. Today we have just derived this, right? Today we have just derived this dimension, right, by using the formula is the dot product of electric field intensity and the del R, which represents displacement. We know that electric field is equal to force per unit charge, so we just put this force per unit charge in the first equation, and we know that the unit of the force is Newton and the unit of the charge is Coulomb. We just put that, right, Newton per Coulomb into meter, since we know that meter is a unit of what, it is a unit of displacement. Alright, we know that 1 Coulomb is equal to 1 ampere into second, and the dimension of the force or Newton was what? It was of course equal to MLT minus 2, MLT minus 2. And this was very important as well. 1 Coulomb is equal to 1 ampere into second. We just put this Newton's dimension in the formula, right? In here, this is the dimension of the Newton. However, this is the dimension of the meter, dimension of this, alright. And of course, down we got the dimension of the Coulomb, which is ampere into second, right? We just simplified it, and in the end what did we get is ML2 T minus 3 A minus 1. Here we have completed our basics of potential difference. In the next video, of course, we will be talking about the relation between the electric potential and the electric intensity. What's relation between them, what will be work equal to when it will be when we will be moving the charge against the electric field. We will be talking about each and everything. I'll be guys telling you the formula for that as well, and that's very easy, very basic. Alright, so here in today's video we have just discussed, or we have just taken out, or we have just derived the dimension for the potential difference. In the next video we'll talk about relation between the electric potential and the electric intensity.